Okay, let's start because we have waited for 5 minutes. So today we will continue our last discussion about the etching process. So last time we discussed mostly about that what are the parameters for etching, and we discussed that what is isotropic and wet chemical etching. So today we were supposed to start the dry etching. Even last time we discussed something about the dry etching. As I told you, first thing that why do we need etching? Etching always comes with the photolithography. Whatever can be done with photolithography plus etching, the same thing can be done with lift-off process as well. So etching is always used to transfer precisely the pattern created on the mask to the wafer or the substrate. So this is why the etching is needed, as we discussed last time. Wet chemical etching, as I told you, that it's very selective, it's cheaper, but the problem is that the high aspect ratio, it cannot be used for very small dimensions. High aspect ratio cannot be attained with the help of wet chemical etching. So that's why we move to the dry etching. So dry etching replaces wet chemical etching whenever we need very high aspect ratio. Okay, dry etching. This is just a flowchart that how the dry etching works. We discussed this flowchart last time, that how it works actually. That first of all, mostly dry etching is anisotropic. It uses ionized gases. Those ions that are actually in the presence of plasma, they react with the surface, and those byproducts, they are very volatile. They are carried away by the carriers, and this is how the flowchart actually tells that H gas flown into the pressure chamber, then plasma is created by the help of RF generator. That plasma ions are actually are bombarded on the substrate, and after bombardment, due to the selectivity film to mass selectivity, there is a reaction between the film and those plasma ions, and those byproducts they are very volatile and they are removed by the carrier gases. Those carrier gases used, they are always inert gases mostly. It may be nitrogen, it may be argon, or some other inert gas used as a carrier gas. So this thing we have discussed last time. This is just a representation of the flow chart, that how the dry etching works. And this is again dramatically representation of the dry etching process. First thing, it's anisotropic, we know. Secondly, that with respect to the film that you want to remove, you need a specific gas that you need to introduce. So it's not like that if you actually if you want to use a combination of sputtering, physical sputtering, as well as the chemical reactor. If you use only the physical sputtering, then you don't need any selectivity. But in that case, it's an isotropic, it becomes isotropic. At the same time, there is no film to mass selectivity. We discussed that thing last time. So reactive ion etching or ion beam etching, they are actually the combination of these two. So they are directional, they are reactive. So you can see that we have positive plate and negative plate, and where your target or the substrate is always at the cathode, that is connected with the negative plate, so that those positive ions or that needs to be bombarded on the target, they move towards the target substrate. So ions accelerated to wafer because wafer is on the negative plate, and different recipes of gases for different targets. So that needs to be selective. The gas you use need to be selective to the target. We will discuss in the next slides that what are the parameters that you need to keep in mind when deciding about that what gas you need to use. Okay, this is again making this thing more clear, that how the etchant ions, they are actually getting reaction with the film that needs to be removed, and those byproducts, they are actually removed with the help of the carrier gas. Okay, so it also says the same thing, that the most commonly used reactive gases usually contain fluorine, oxygen, and chlorine. So you will see that the gases that we use for dry gases, mostly they are fluorocarbons. That is, it contains carbon, it contains fluorine, because fluorine is very reactive. You know that the 7th group, they are actually most reactive gases. Okay, so due to their high reactivity, we use that. Chlorine is mostly used for etching aluminium. Aluminum is mostly aluminum or even aluminum oxide, Al2O3, that is also removed by chlorine. But fluorine is mostly used to etch silicon as well as silicon dioxide. You may have seen in the lab that we use HF to etch away silicon dioxide by using the wet chemical etching. So fluorine is used to etch silicon and silicon dioxide both. Types of plasma system, that how the plasma is generated. There are 3 types how you actually can generate the plasma. First thing, that is capacitive coupled plasma. That is, the electrodes are directly electrically coupled to the plasma. In that case, high electric field is performed and power transfer is efficiently. And the important thing is that the plasma that is generated, that is very uniformly. The second thing, that the second method, that is actually inductively coupled plasma. In that case, you don't have the power electrodes directly coupled to the plasma, but in that case the power is transferred through induction process, just like in transformers, that you don't have the physical coupling, but it's just the inductive coupling. So just like in transformer you induce voltage, similarly this is also the second way that you can generate the power. The power transfer is also very efficient in this case, but no electrodes exist inside the plasma in inductive coupling. And the third method is actually wave heated plasma. In that case, you use electromagnetic waves to generate that power. So that again, you don't have the electrodes physically existing in the plasma, but by using electromagnetic waves, you generate that plasma. So these are 3 ways. You can use any one of these 3 because, I mean, it depends on what equipment you are using. So all 3 of them are very efficient in transferring the power, but the last 2, they generate high powers as compared to the capacitive coupling. So it depends on the equipment. Any one of these 3 would be applied in that equipment that you are using. So plasma. I believe that we are talking about plasma again and again. I hope that you know what is plasma actually. Anybody who knows what is plasma can define how you define a plasma.
Ionized gas.
That is ionized gas. Very simple answer. That is, it's in the gaseous form, but it's ionized. It's partially ionized gas, to be more specific. And what is the benefit of plasma over a gaseous phase gas?
It's highly reactive.
It's very energetic, it's highly reactive. So when you have plasma, it means that whenever you have plasma etching, plasma dry etching, in that case it means that etch rate would be high. Whenever you have the plasma, due to its energetic nature, due to highly energetic, it reacts faster and etch rate is high. So plasma is just the partially ionized gas, and degree of ionization, because I said it's partially ionized, so there would be some of the molecules that get ionized. So degree of ionization for any plasma is always equal to number of charged ions divided by the total number of molecules. That is, that how many, what percent of the molecules have been ionized. Okay, so this is usually what happens in plasma. You can see that
what is the degree of the ionization again?
and as I said, it's partially ionized.
Yeah.
So you can see there is formula is written here, over there. The degree of ionization, number of charged ions divided by original number of ions, atoms or molecules.
Okay, so it's a percentage.
It's like a percentage, but you don't multiply with 100. So that's why I said it's what percent is, what is the ratio of charged ions to the total ions? That is the degree of ionization. Okay, in plasma, as you can see that first of all, whatever the gas you are using, CF4, that is tetrafluoromethane, as I told you, is one of the most widely used gas to etch silicon as well as silicon dioxide. So CF4 is used to etch silicon as well as silicon dioxide. We'll see later on that these are some of the processes that can the plasma undergo. In the presence of plasma, the dissociation can occur, ionization can occur, and recombination can also occur. So you know this thing. Dissociation means that you actually dissociate the molecule in two parts. Ionization means that you extract the electron to make it ionized, so that it becomes more energetic. And recombination means that those highly energetic positive and negative ions, they actually recombine with each other again to get unenergized or low energetic molecule. So that is recombination, is actually the reverse of ionization or dissociation. So I will discuss that when recombination actually comes into account. Okay, so here we can I can tell you that what are the parameters before. First of all, you should know that what are the parameters that control the etch rate in dry etching. What do you think? What are the parameters? I mean, what are the parameters that can vary the etch rate in dry etching?
Degree of ionization.
Sorry?
Degree of ionization.
Degree of ionization, that is how reactive the gas is. Anything else?
Pressure, temperature.
Yes, temperature. So temperature can change, pressure can change. Pressure means that higher the pressure, higher would be the etch rate. Because in that case, actually, you are providing more and more etchant. The number of etchants are increasing. So, in addition to that, nature of the surface means how selective, how much reactive, how fast it reacts with that. Yes.
Removal of the residues.
Yes, that is actually one of I would be discussing, but the loading effect, that is one of the part of the loading effect. So right now, out of the parameters, as he has indicated, that pressure is also one of the parameters. In addition to that, the surface temperature, nature of the surface, and geometrical aspect of the surface, that if it's very deep trenches, in that case, of course, the etch rate would be smaller, but if the area exposed is high and number of etchant is, I mean, the source is unlimited. So, in case of pressure, what happens? Maybe that's where actually recombination comes into account. If you have pressure on the x-axis and etch rate on the y-axis, what we think that by increasing the pressure, etch rate should increase, right? It looks like because higher the pressure, more would be the number of etchants. But what happens? It's like this. Because initially, yes, it happens that when you provide more number of etchants, in that case, the etch rate increases. But up till a certain level, the etch rate keeps increasing. After that, what happens? If you increase the more pressure, means you are introducing more number of etchants. So this recombination comes into
Can
effect.
you offset that by degree of ionization and temperature? Like, is there a surface that kind of goes like this with the high pressure, high temperature still etching faster?
I couldn't get your point.
So you increase the pressure, you increase recombination, etch decreases. But if you also increase the temperature,
Just let me make it clear that by increasing the pressure, the etch rate increases, but up till a certain level. After that, it starts decreasing. Okay, now what's your question?
So what I'm saying is, let's say you're at the right side of that graph. Can you make the etch rate even faster than it was before by also increasing the temperature.
Oh, okay. So you mean to say that when the pressure is very high, you can increase that rate by using some other parameter? Yes, you can do it.
Because pressure gives you more per unit area.
It's always a combination of all parameters. Just like, for example, if you remember, I'm doing oxidation. I have 100 instead of 111. So etch rate would so the oxidation rate would be low. The growth rate would be low. I'm taking that example. You increase the temperature. So by increasing the temperature, you know that you increase the growth rate. So like the same thing is here, that if you that's why whenever you need to see the effect of one parameter, you always keep all the other parameters constant. Experimentally, you vary only one parameter.
So my other question is, what happens to a silicon? What's the end product of this etch reaction?
What happens to silicon?
Yeah, when it's etched, does it become a gas? Is there a liquid or a solid product that must be removed?
Okay, we'll discuss in the next slides that what exactly happens. But of course, I'll say that the byproducts are becoming gaseous form. They are volatile and they are carried out by the carrier gas. But they're actually this is two-step process in some cases. That it becomes a skin layer SF2 and then it becomes volatile. I'll explain that. So right here, why I wanted to show this thing, that this part shows that recombination process. When pressure is increased, number of agents has increased so much that they start colliding with each other. So due to high collision between the agents, they themselves collide with each other, they themselves start recombining. Due to recombination, we lose most of the agents, so again the etch rate starts increasing. So that's what I wanted to tell you guys. Similarly, temperature, it can increase the etch rate as well, but it also increases up to certain level. After certain level, it becomes constant. After that, temperature does not increase it that much. But due to the temperature or even pressure, you always need to keep in mind that if you increase the temperature, that the mask or the substrate, that should not be damaged. So you always need to keep while increasing or while defining your recipe, you need to keep in mind that what other elements we have on the surface. Just like if I have some metal on the surface, I want to increase the temperature so that that metal melts away.
So RIE reduces your thermal budget, is that what you're saying?
RIE, so far as heating is concerned, it's always, it's not at high temperature, it's always at low temperature, even I would say room temperature. RI is just the bombardment. And there is chemical reaction and there is the energetic bombardment. There is some electric potential, but no heating is there.
So,
but just if in some case if you can heat up the substrate, it can increase the etch rate. This is what I'm saying. So if the temperature of the substrate is different, the etch rate would be different. That's what I mean to say.
So I have questions. So can you read the slide?
Yes.
There's 5 reactions, and I think 2 reactions, excitation and dissociative ionization, are the only thing generating plasma. I mean, improving plasma, right?
Excitation and
dissociative ionization.
And dissociative ionization, yes.
And the other factor, only 2 factors is increasing plasma gas, right?
Okay, these are in excitation. You can see that electron is not removed. That just CF4 is still CF4, but it gets into excited form. So it becomes more energetic. Whereas dissociative ionization, you can see that what happens out of CF4, we remove one fluorine atom. Fluorine is itself very reactive, and another one electron is removed. So due to that electron, CF3 is positively charged. So it's not in excited form, it's in ionic form. In excitation, it's not in ionic form, you can say that is star, not positive. So that is in excited form. So but all this, you are right that in ionization or in excitation, you are actually making that gas more energetic. So except recombination, everything is actually making it more energetic. In recombination, it's the reverse. That energetic particles come together, they recombine and form a low energy molecule, that is
I
CF4.
think that is related to the concentration.
Yes, recombination comes at a very high concentration. That's why I said when at low concentration, recombination won't come in, and but when is there high concentration, number of agents increase. So in that case, they start colliding with each other. So they start recombining as well. Okay, as I told you that for different solids or for different materials, you need different gases, and these are the different gases that you can use for different films. As I told you that CF4, where is that gas? Yes, CF4 is for silicon and silicon dioxide both. You can see that chlorofluoromethane, CF4, the first gas, and in that case, if you see the Etch products, that is SiF4 and Si2F6. Okay, so actually these are three different combination that can happen. That CF4 is broken down into we can after reaction with the surface we can form SiF2, SiF4, Si2F6. These are three different forms that you can get. But why you see that Etch products, that is the byproducts, that shows only these two. It does not show SiF2. That also forms in result with when fullerene reacts with silicon, so SiF2 also forms. That is energetic fullerene or fullerene ions. They are actually, I would say that first, this is the first product that becomes. When more fullerene ions react with that, we get to this form. So initially this is SiF2 that is formed. So the answer is that only these two are the volatile gases. So these two are in the gaseous form. They can be carried away by the gases. It resides, SiF2, it forms, but it resides on the surface of the substrate. It does not gets into the gaseous form. It gets there just like a skin on the wafer. But it can be removed. How it can be removed? I just answered that a couple of minutes before. So this SiF2, when initially fluorine reacts with the silicon, we get SiF2. But that SiF2 that resides on the surface, it's not volatile, it does not get removed from the surface. So what happens? More fullerene ions, they keep bombarding on the surface. So when they bombard this thin skin of SiF2, they convert this SiF2 to SiF4 or Si2F6. So this is converted to any one of these two and gets removed. So this is how it's removed. So somebody may ask, okay, in dry etching, SiF2 is formed and it resides on the surface. How do you remove it? Okay, so it's not removed. You don't need to say that we wash it electron or something like. It's automatically removed because SiF2 is converted to SiF4 by when it is reacted with more fluorine. Okay. We'll discuss that later on as well. Okay, let me tell you about F by C ratio as well. Because we are talking about chlorofluoromethane, CF4, and I told you in dry etching mostly you use, as you can see this, CF4, and there would be CF3 as well, there would be CCl2F2. So there's the chlorine, fluorine, and carbon and oxygen. These are a few of the gases that are mostly used. So chlorofluorocarbons, they are very widely used for dry etching. So that's why there is one thing named as F by C ratio, FC ratio.
What happened to the C and the CF4? The fluorine became SiF4 and SI. What happened to the carbon?
Carbon of
CF4.
Tetrafluoromethane.
How? I mean, where does it go?
actually carbon also reacts with if we introduce, sometimes we introduce oxygen. If we introduce oxygen, carbon forms CO or CO2, and they are also very energetic, and they increase the even H rate is increased. So that's what I was going to discuss. First of all, you should know, you will come to know how that C is actually used. FC ratio is very important. Higher the FC ratio, higher would be the H rate. That's the simple law. That is, higher the FC ratio, higher would be the H rate. So it means that if we talk about CF4, what is the FC ratio? That is 4:1. So it's simply FC ratio means that the ratio of fluorine atoms to carbon atoms in one molecule. So with respect to FC ratio, you should be knowing about effect of adding oxygen or hydrogen. So we will discuss, I'll let you know that how FC ratio is actually disturbed by adding the hydrogen or by adding oxygen, and after that how it actually affects the H rate of silicon and silicon dioxide. We will discuss in the next slide. Okay, so silicon H chemistry, you can see that H rates are given in angstrom per minute, and just to figure out that what will be the film to mask ratio, the photoresist H rate is also given, so that you should know that okay, whether I can use photoresist as a mask for this process or no. For example, if I want to etch polysilicon, I cannot use photoresist, the first line, I cannot use photoresist as a mask, because photoresist has got higher H rate than the polysilicon. But silicon dioxide, yes, I can use CH4 plus CHF3 plus helium under these conditions. I can use to etch silicon dioxide, I can use photoresist as the etch mask, because silicon dioxide is having approximately 3000 to 4000 angstroms. That is much higher as compared to photoresist H rate. So this is a table just to give you an idea that what are the gases and what are the corresponding H rates that you can achieve. Okay, so it talks about the dry etchants. As I told you that free fluorine radicals, they are very energetic and they are mainly responsible for silicon etching. Fluorine reaction with silicon is spontaneous, does not need any bombardment. But in this case, if you don't bombard it, in this case, as I told you last time, it won't be directional, it will be isotropic. I mean, if it's low energetic, you don't bombard it, you don't get it directional. So that's why we use chemically reactive as well as under bombardment process as well, so that a combination of those two can be used. Okay, fluorine-rich polymer deposited, that is, we'll discuss later on that it's just a way you deposit fluorine-rich polymeric layer on the side, so that that layer may work as a passivation layer, and it does not to actually for the purpose of deep reactive ion etching. So we use that polymeric layers in DRI. We will discuss it in DRI. So that's why Dr. Bora also has talked about that. It will be discussed in deep reactive ion etching. these polymeric layers, they are deposited in the well, and after that what happens, we remove that layer from the bottom, we don't remove it from the side, and when we etch it, because there is a passivation layer on the side, no passivation layer is present on the bottom, so what happens that you get more deeper and deeper, so that is deep reactive ion etching. Okay. The chemical portion of the etch reaction can be described as a number of discrete steps. This is just giving you a flow chart that how the gas comes in. After that, you bombard it in the presence of plasma, and with the help of pump, you take out the byproducts with the carrier gases. Okay. So here, in this slide, we are discussing the same thing that I left there because I knew that in the next slides we will be discussing that. You can see fluorine atoms penetrate surface and react with, first of all, surface forms silicon fluoride SiF2 like skin that does not readily dissolve. So you can see that underlying thing, as I told you, that after the CF4 is dissociated into CF3 and fluorine, those fluorine ions or even fluorine molecule is very reactive, that gets in reaction with the silicon surface, and initially SiF2 is formed. I just described that. So that SiF2 is just like a skin that does not readily dissolve, and fluorine atoms penetrate surface, this thin surface, and they react with this skin, that is SiF2, to form SiF4 or Si2F6. So they are actually in the volatile form, and they can be removed from the surface. And this is the diagram that shows that how actually SiF2 forms, and after that, by bombarding more fluorine atoms, you can get SiF4 that is volatile and removed by the gases. Okay, here comes that what is the effect of oxygen, adding oxygen and adding hydrogen on the etch rate. So, okay, FC ratio. First of all, let's discuss that what is the effect of adding oxygen. If I add oxygen in any chlorofluorocarbons, I am taking CF4 as an example. If I add oxygen, what will happen? The bottom line reaction would be that oxygen will consume some of the carbon to form CO or CO2. Anything can be formed. Okay, so when we add oxygen, carbon is consumed. What happens to F, fluorine? That remains the same. Fluorine atoms are not reacting with oxygen. Carbon atoms are reacting with oxygen. So some of the carbon atoms get consumed. So what do you think about F by C ratio? FC ratio, that should increase or that should decrease?
It will increase.
That would increase. Of course, when C has decreased, but F is the same, so FC ratio increases. When FC ratio increases, it means your H rate, that also increases. So H rate also increases, and whether this is silicon, whether this is silicon dioxide, irrespective of silicon or silicon dioxide, the H rate increases. But let me tell you that H rate is maximum. It's not like that you can add as much oxygen as possible and H rate would be maximum. H rate would keep increasing. It's not like that, because of course the FC ratio increases. It would increase by the time when there is some C to get reaction with the oxygen. If I have 10 molecules of carbon and I add 200 molecules of oxygen, so do you think after 10 molecules of oxygen the rest of the molecules will have some effect? No. You add more oxygen, but there is no carbon that can react with the oxygen and increase the FC ratio. So there is certain limit.
Wouldn't the reverse be occurring, that oxygen will react with silicon to form SiO2? Can that happen?
Actually oxygen reacts with silicon dioxide to form, with silicon to form silicon dioxide after 900 degrees centigrade at room temperature, because I told you this process reacts at room temperature. At room temperature, it takes maybe 10 minutes or 15 minutes. In 10 or 15 minutes, you don't get any native oxide. It's just like a native oxide or something. So you need the high temperature, more than at least 950, to get the silicon dioxide if you're thinking about the growth. Okay, so it means that maximum when oxygen is 20% by concentration. After that, it remains constant. After that, it has no effect. So if you add oxygen, F by C ratio increases, but you cannot add oxygen more than 20% by concentration in that chamber. You got confused? Didn't get my point? I was saying that adding oxygen increases FC ratio, so that actually increases the H rate. Okay, up till this
until
is clear.
it starts diluting the fluorine, right?
Sorry?
Until it starts diluting the fluorine.
No, the fluorine is not affected. It means same. It's not affected by adding oxygen. This carbon was getting affected by adding oxygen. Okay, until that oxygen is disturbing or is consuming this carbon, it would be affected. But after 20%, introduction, 20% by concentration, the oxygen is no more effective towards the consumption of carbon in that FC ratio. This is what the point is. So the maximum increment of the H rate due to the change in FC ratio is when oxygen becomes 20% by concentration. If you increase more than 20%, it would remain constant, there would be no effect. Okay? So after that, now we talk about, so adding oxygen increases the H rate, and it increases the H rate for both silicon and silicon dioxide. This is what we concluded. I'm explaining in detail because sometimes in the final exam or even somebody may ask you that what is the effect of, it's very commonly or widely asked question that what is the effect of adding oxygen or adding hydrogen, and what is the effect on the H rate of silicon and silicon dioxide. So H rate of silicon as well as silicon dioxide increases by adding oxygen. How about adding hydrogen? First of all, adding hydrogen. Do you think hydrogen should react with fluorine or hydrogen should react with carbon?
Fluorine.
So hydrogen actually reacts with fluorine. So then fluorine reacts with hydrogen, we get HF. Okay, so fluorine is consumed. How about F by C ratio? In this case, it decreases. Okay, up till here it's very clear that adding oxygen, FC increases, adding hydrogen, FC decreases. But the difference starts from here actually, that FC decreases. So what do you think about the H rate? When FC decreases, H rate should also decrease. I told you it's a general law that higher the FC ratio, higher will be the H rate. So H rate decreases. But does it decrease for both silicon and silicon dioxide, or it decreases only for one of the two? That's the difference.
Decreases only for silicon. So H is SiO2.
That's actually the point. That the FC ratio decreases. If I talk about the H rate due to my etchant, that is CF4 for example, etchant gas, the etch rate due to the dry etching process, due to my etching dry etching process by my etchant, that actually decreases. But for silicon, FC ratio is less, so the etch rate would decrease. But so far as silicon dioxide is concerned, whatever F has converted to HF, that is also contributing to etching silicon dioxide. So the etch rate for silicon dioxide, that does not change. Okay, F by C ratio decreases, but etch rate does not change for silicon dioxide, but etch rate decreases for silicon. Okay, so in this case, you got this point, that for silicon dioxide, adding hydrogen does not change the etch rate. If somebody asks what is the effect on etch rate of silicon dioxide by adding hydrogen, so answer is it remains same. And if it says that what is the effect on silicon, so that goes down. So similarly, as in case of oxygen, the etch rate would be minimum, because in this case the etch rate is actually affected only for silicon. So we will talk for silicon only. So etch rate for silicon is minimum. For silicon, the etch rate is minimum when hydrogen is actually 40% by concentration of that. At 40%, the etch rate is approximately 0 for silicon. But of course, for silicon dioxide, it does not affect.